Hello and welcome to my presentation Use of Thick Heavy Plates for Bridge Constructions. My name is Tobias Lehnert and I'm responsible for the technical support in steel construction applications at Dillinger, a German steel producer. In many projects and since many years, the new possibilities which the steel industry brought up were used and somehow enabled innovative solutions in bridge constructions. One example is the railway bridge over the Neckar, where longitudinal profiled plates were used. Another nice example is the Samuel Beckett Bridge, where high-strength steel up to S690 was used. And it is especially these modern and innovative steel bridge designs which, on the other hand, challenge the steel industry and push them to move on in their developments and to further develop. And of course, the steel industry is willing to follow these needs of the steel construction industry. And so how can heavy steel plates and especially thick plates help in a bridge design, for example? In general, steel is already the optimal material for bridge construction due to its high sustainability. Steel is 100% recyclable and has a very high raw material efficiency. And one trend which we now see in steel bridges is the trend towards larger thickness plates. For example, in the application in thick flange plates. And the reason for that is clear. It helps to avoid the fatigue critical lamella joints, which then fastens the installation of the bridge, especially due to the much faster on-site welds. But another application is of the thick plates is the thick plate trough bridges, which we see nowadays in railway bridges. Here, the thick plate is the essential and the main component of this bridge. But if nowadays one wants to design with thick plates, there are some challenges which needs to be respected. The first challenge is the weldability. And I think it is quite known, the larger the plate thickness, welding can be a challenge. Another challenge is the brittle fracture analysis. And here, for example, the Eurocode in the part 10, in the table 2.1, gives maximum acceptable thicknesses. So if in your design you would benefit from a larger thickness, but it is not possible according to this table, there needs to be found a solution. There needs to be a solution for that. And the third challenge which can come when you're designing with thick plates is generally the availability of thick plates, and especially if you need large formats. So now in this short presentation I want to go through some of these challenges and bring possible solutions. You will find in the paper a more detailed a more detailed explanation for all these challenges. So the first challenge, weldability. If we speak about weldability, we have to look on the carbon equivalents. As the carbon equivalents, they are a measure for the weldability of a steel plate or steel in general. And if we talk about carbon equivalents, there are different general trends. The first trend is if one wants to increase the strength, the carbon equivalent also goes up, and by that the weldability goes down. So in general, a low carbon equivalent means good weldability, a high carbon equivalent means worse weldability. And this can clearly be seen on this diagram here, where you have the yield strength and the carbon equivalent. So looking now at the blue curve, for example, if one wants to increase the strength, the carbon equivalent will increase, and by that the weldability will be worse. Another general trend in the steel industry is if you increase the plate thickness, usually also the carbon equivalent will increase, and by that again the weldability goes down. And unfortunately, it's a fact that both of these trends are nowadays seen in steel constructions. One wants to increase the strength and one wants to increase the plate thickness. So there definitely needs to be found a solution. And actually there is a solution. And this solution is already seen here in this diagram. So if you look on the red dots, the red line, which is the thermomechanical or so-called TM steels. Thermomechanical rolling is a special production process which creates a very beneficial steel material. And it can be seen here that achieving the same yield strength as for 60, for example, is possible with a much lower carbon equivalent, and by that with a much better weldability. But the problem so far was these TMCP steels were in the old EN 10025 part 4 only defined up to 120 millimeters, and they were also only available up to that thickness. So if the thickness exceeds 120 millimeters, which can occur in a bridge design, a normalized steel or a quenched tempered steel had to be used. And these steels, they have certain disadvantages. The normalized, as you have seen on the slide before in the diagram, they have a much higher carbon equivalent, so the weldability is worse. The quenched tempered steel, they also have a higher carbon equivalent, but they additionally have higher costs in production. So both are options with disadvantages. But the good thing now is that since the revision of the EN 10025 part 4 in 2019, end of 2019, TM steels up to 150 millimeters are now defined, and they are also available on the market. And this gives a lot more potential for the application in bridge designs of TMCP steels. So what are the advantages of these TMCP steels? So why are they so beneficial? It's quite simple. It is the lower carbon equivalent. This lower carbon equivalent has as a conclusion an excellent weldability of the steel. And that means no or less preheating when welding. So even in very large thicknesses from the steel material, these TMCP steels can be welded without or with very less preheating. And this is clearly be seen on this diagram where we have a comparison of an S460 steel in the normalized condition compared to a TMCP condition. And it's clearly seen how this shift in the delivery condition decreases the preheating temperature. So that's it's an important advantage, not only regarding the cost and time savings, but also with respect to job safety, if, for example, a very narrow girder has to be welded. And there are additional benefits. For example, these steels are nowadays available as with an option with a constant strength properties, so constant strength independent of the plate thickness, even up to 150 millimeters. So if a steel is ordered according to the normal standard, this blue line will be the case regarding the strength. But nowadays, even this violet flat line is possible and can be ordered as an option. And this gives additional potential for designing in bridges. And especially these high strength, very thick plates are, for example, used in skyscrapers in the Middle East, where we have, where you see here now two very nice projects where S460ml up to 150 millimeter with a yield strength exceeding 460 megapascal was used. And somehow that's the world record regarding thickness for TMCP. So very nice applications already used. Now coming to the second challenge, the challenge with the brittle fracture analysis. Here there is a picture of the table 2.1 from the Eurocode part 10, Eurocode 3 part 10, and you can clearly see that for higher utilization rates and lower reference temperatures, and now let's say we use a steel S355, the maximum applicable thicknesses are quite low. And this can become a challenge when designing a bridge. So what could be a solution to that? When looking for the solution, one first has to see what was the input to this table. And of course the input to this table were the steel grades defined and available in the material standard with their toughness properties. So the toughness properties of these steels went into the calculation, and this table was the result of the calculation. And it were all the steel grades that are defined in the EN 10025 were used in this calculation. But nowadays, even steel with better toughness properties are possible to be produced and are available on the market. So the interesting question now was, what if we use these better toughness properties as an input in this table? What would be the outcome? And here we see the result. And it's quite obvious and quite clear that this will bring a lot of potential. So for example, if we now again come to an S355, if we input as an input, we use the standard requirement of 27 joules at minus 50 degrees Celsius and a high utilization rate and reference temperature of minus 30 degrees Celsius, we will end up with a maximum acceptable thickness of 75 millimeters. If we now increase the toughness properties to, for example, 50 joule at minus 60 degrees Celsius, which is available on the steel market, then these thickness will be increased to 110 millimeters. That gives a lot more options in the design. You will see this table also in the paper, and also there's a additional table which gives showing the increase and the difference which is possible. So there are increases up to 50 millimeters possible, and that shows the large potential which this additional supplementary toughness requirement could bring to the brittle fracture analysis. But it is very important, of course, these needs to be ordered and these needs to be inquired at the steel producer, so that the steel producer can produce the steel so that it fulfills this larger toughness, or this more severe toughness requirement. But my personal opinion is that this will bring a lot of benefit, for example, also in the thick plate trough bridges. So with this short presentation, I now want to sum up a bit on these challenges which we see. So if we think of the weldability, TMCP steels are the ideal solutions, and they are now available up to 150 millimeters, in some cases even exceeding this thickness limit. Regarding the brittle fracture analysis, an extension of the EN 1993 Part 1 Part 10 Table 2.1 is possible when specifying improved toughness properties already in the inquiry or in the design. And availability of large formats, I didn't go into detail here, but due to new pre-material, plate weights up to 42 tons are nowadays possible, and by that, even in large thicknesses, large widths and lengths are still possible. And with this short summary, I want to thank you very much for your attention, and I'm ready to any questions either now in the chat or even via email. And thank you again.